today we'll welcome Pani, a first year PhD student at University of Bath. Currently, he's working on causal and graph-based methods in reinforcement learning. So, he will be presenting his work on curricula for learning robust policies with factor state representation in changing environments, which was accepted at European Workshop on Reinforcement Learning 2024. Pani, the floor is all yours.
Right, thanks for the introduction, Rahul. Yeah, I'll try to break down the title so it's easier by introducing first the three components that make it up. That is the curriculum, robust policies, what we mean by that, and what are factor state representations. And then I'm going to get into the paper explaining what exactly we did. So to start with, curriculum learning is a learning strategy where the idea is to structure the learning process with tasks of increasing difficulty in order to improve the learning speed or improve the final performance. For example, in the example you see here, it's called quick chess. It's a version of 5x5 chess. We could train a reinforcement learning agent using only the pawns, what you see on the left, which is a simple version of the final task you can see on the right. And then over time, we can introduce, for example, more pieces like the king or the queen or something like that. Right, so this is curriculum learning. Then robust policies. So the problem of interest in this line of work, in this paper and in my work is in generalization. I'm going to use the definition of generalization from a paper I reference here, which is a survey on zero-shot generalization. The idea being that if you train on an environment and then you test on the exact same environment, and by exact same environment, we mean the parameters that you use to create the environment are exactly the same, then this is what's called singleton environment. An example of that would be, for example, any simulation where you have a robot. If you have, for example, let's say a parameter could be the gravity or a mass of the hand or the length of a leg and something like that. So if you train and test with the same environment, you have what's called a singleton environment. If you train and test with similar distributions, for example, you sample the length of the leg from the same uniform distribution in training and in testing, you have what's called IID generalization, so that your environments are independent and identically distributed. And then OOD, auto distribution generalization, is when the train distribution and the test distribution of the parameters of the environment don't match. This is what's most interesting. And the reason that that's interesting is that in the real world in general, the real world is non-stationary, so there are constant distribution shifts. So this is why OOD generalization is interesting to me, but generally, I suppose, to the research community. Right, and then lastly, factor state representations. So the idea with factor state representations is that you can see on the left there is an image of a task called frozen lake. It's a very simple task where you have an agent that needs to reach the present by going up, down, left, or right. The agent gets a minus reward for falling into the hole, so plus 10 reward, I think, for getting into the present, and some small negative reward for moving. Now, there's a reason I introduced the task because I'm going to use it later. It's good that you understand what it is. So the image you can see on the left, it has high dimensionality, has lots of pixels, and also the pixels themselves are not very informative. So it's a low-level representation, but it's high-dimensional. Well, as you can see on the right, there is some so-called factor representation that is very high-level and very low-dimensional. For example, the number of bits we need to store what's on the left is much less than what we need to store what's on the right. And also, I should note that the representation on the right is not minimal. Obviously, we can get rid of the grid size because you can read it from the whole locations. You can get rid of the whole locations because you can see them from the distance matrix. It's not really important. It's just a demonstration of how you can factorize a particular state. And generally, factor state representations are thought to improve sample efficiency of algorithms and have better generalization of abilities. Right. So now we're ready to talk about what the paper is really about. So in this work, we investigated some simple curricula to learn robust policies that generalize well in environments that change all the time. And we used factor state representations. Right. So I'm going to go back to the frozen lake example. Let me first check if there is any questions here. No. Good. I'm going to go back to the frozen lake example. In this work, we introduced a new environment called shifting frozen lake, where the idea is that over time, on every single episode, some of the variables can change. The variables that I put a star in. So the cell of the grid that the agent starts in can change, the final goal location can change, the whole locations can change, but it's always guaranteed that there is a path to get to the end. And the idea here is to try to see what kind of curricula help the agent to learn best, and how do factor state representations help with that. Cool. So just to give you kind of an idea, this is not exactly what happens. I'm going to explain in detail what happens, but just to give you an idea of what I mean by shifting, let's say you sample an initial environment, which is the one you see on the left part of the screen. You could change the goal location, which is the top image here. The goal is moved 1 square to the top, up. You could change the grid size. You could change the whole locations. You can change the start locations. Now, it's not necessary that this changes on every episode. It's not necessary that on each episode only one of them changes. This is just kind of an illustration for you to see. Cool. And then, as I said, this kind of can represent the fact that on each episode we can have a shift of some of these variables, can represent that the real world is non-stationary, and we can use it to design some sort of curriculum for the agent, basically. Right. So these are the environmental shifts that the environment supports. I'm going to explain what they are, and then I'm going to walk you through some sort of experiments with it and what conclusions we made from them. So no shifting just means there is a single environment. That's just the same thing as training on a single environment with single parameters. Random shifting is domain randomization, which means on every episode we uniformly sample every single one of the variables. Single preset variable shifting, there is a preset variable that on the start of every episode we change. For example, on every episode we change only the grid size, or on every episode we change only the agent location. Single random variable shifting, on each episode we sample one of the 4 variables, and then we change that variable. So on the first episode you could change the whole locations, on the second episode you could change the grid size, etc. And stored example shifting means we sample, let's say, 10 or 15 examples, so environments, and we shuffle through them during training. I mean, shuffle through them. We randomly sample one at the start of each episode. Cool. Now, for these experiments, we used the random action selection agent, which is just to serve as as just like a baseline, basically, an optimal agent, which is always possible in this case because you can run a BFS algorithm, a breadth first search, and find the optimal path. And the PPO agent on top of the state, and the PPOF agent, which is just PPO on top of a factored state representation. The reason that there are no value-based methods here, it's that we had the same conclusions with them, like with DQN, for example. It's just that the diagrams were very cluttered with them. And yeah, it was clear to just include PPO in this case. Right, cool. So the first experiment we did, these sort of experiments have a similar format. They always have a dotted line, which represents changing from training to testing. And on each side, there is usually a different behavior of the environment. For example, in this case, on the left side, we have no shifting, so it's a single example. And on the right, some shifting. So on each episode, we sample, again, a new environment, basically. We sample all the variables. Now, another thing is we use epochs here. Epochs are, in this case, 900 time steps. And we run, I think, 10 agents, and we display the standard error here. Another thing that's important to mention is that, as you'll see on the left-hand side, the methods performance says don't match. They're not the same. It looks like they don't manage to fit perfectly the single example, but they do. The reason that this happens is that if the example that they sampled is different, then if, for example, you have a 2x2 grid versus a 10x10 grid, you'll get way more reward in a 2x2 grid because you'll manage to get to the end way more times. So this is just a byproduct of not training on the same example, basically. And this will come up a lot because, yeah. Right, so on the left-hand side of the dotted line, the methods fit the single example. And then after the distribution shift, we change to like random shifting. We see that none of the methods actually does any knowledge. There is no knowledge transfer, really. I mean, over time, it looks like PPOF tries to learn the policy and eventually manages to reach the optimal policy. But yeah, and PPO also doesn't ever manage to reach the optimal policy. The interesting thing here also is that because in this task, you only get reward when you reach the present, a positive reward. I mean, you get a negative reward for moving and a big negative reward for falling into the hole. A really good strategy, which is represented by a small negative value, which is what PPO achieves here after the shift, is just going left and right, or just going into a corner and just spamming, staying in the corner forever. And the reason is that it's a less risky strategy. And the bad thing about this is that if you never manage to get to the end, you're never going to learn how to solve the grids. Yeah. So nothing good here. In the next experiment, we did something a little different. We again fitted a single example, and then we changed to changing only a single variable after the distribution shift. We change a single variable on every episode. So on every episode, we sample a variable, so one of the 4 variables, and then we sample its value. And again, training only on a single example, none of the agents, PPO or PPOF, demonstrated any knowledge transfer. I mean, PPOF was able to quickly learn a good policy, but yeah, that's besides the point. And then what is usually done in reinforcement learning, domain randomization, we train with we trained the agents with basically sampling a different environment at the start of each episode, and PPOF managed to learn a robust policy, maybe not the optimal policy, and PPO got stuck again on this left or right behavior. I'm going to use this to basically compare the other curricula too. Yeah, I did want to say something, but okay. Right, so first thing we did here was we asked ourselves, do we really need to sample a new environment on each episode? Or maybe we can sample 10 environments or 15 environments and just only use those environments, and maybe we can still generalize well. And the answer was yes, with the PPOF agent on top of a factor state representation. So the idea was that we trained with the stored examples up to the dotted line. And then after the dotted line, we did a domain randomization, random shifting again. And we saw that we got a good robust policy, which was also improved quite fast, but was also comparable, as I will show later, to just training on a different example on every episode. Another thing we did was we, oh yeah, I forgot. So we wanted to also find what's the golden number, if you will. What's a good number of examples? Obviously, this would vary from task to task. But yeah, for this particular task, we said, what if we had one example? What if you had 5 examples? What if you have 10 to 13, 25? And we saw that the performance basically doesn't increase much after 13 examples. But it takes longer to fit the examples, the more examples you have, basically. So this kind of is a balance of performance and sample efficiency, and also learning fast. The next question we asked was, what happens if we change only one variable? So ignore the title here. This is for the next slide. But the experiment we did before is we fit a single example, which is what you see on the left, and then we changed only one variable, and we saw that 3 of the 4 variables caused high regret. It's the 3 that you see big drop in performance, basically. And then we said, okay, what if we train the agent by changing only that variable, only the variables that cause high regrets? This is what I mean by single preset variable shifting. You choose one of the variables, and then you shift only that variable during training. And interestingly enough, 2 of those 3 variables also produced robust policies, which, as we will show later, are also comparable to the domain randomization. I should also say that all these things only work over factor state representations in this task. Right, so let's look at how the different curricula compare. So I'm going to talk a bit about this diagram here. The vertical line, again, is the shift. So before that, we use the curriculums that I explained. I'll go through them one more time. And after that, it is just we sample a new environment on each episode. So this is supposed to signify training and testing, basically. And the horizontal line signifies the stack behavior that I talked about of going left and right, or being stuck in a corner. So the top, I have 5 curricula here, A, C, D, and 2E. The A is using just a single example, which, as you would expect, it drops down to that stack behavior and improves slightly over time. And then the other 4 are the curricula that we talked about. Random shifting, which is just domain randomization. Stored examples is using just a few examples, like in shuffling through them. And then the whole holds variable and goal variables curricula is we only change that variable during training because it caused high regrets while in the previous experiments. So what we see here is that one of the E curricula, the D curriculum, and the C curriculum have comparable performance, basically. But yeah, even though there is a bigger drop in performance in C and D, they managed to reach the same performance as domain randomization. And I should mention also here that domain randomization here does, we're testing for IID generalization, while the other ones are out of distribution generalization. Now you might also observe that there is a big gap here between optimal performance and the performance of those curricula. And over time, indeed, those curriculum, they don't reach exactly the optimum, but they get higher than this. There is a way to reach them, to go from where it is now to the optimal one, but I'm actively working on it, and it's not part of this paper. But if you are interested in this, talk to me. Right. So another thing we looked at, which is maybe a bit unnecessary, but we also compared, we basically plotted the regrets of the different policies. And we kind of wanted to see over lots of runs, what is the regret. And as expected, we saw that the policies that perform best are the ones that take the most risks in this task, which I guess means not going back and forth. Right. So some closing thoughts here. What we studied in this work was how, if you use factor-study presentations, you could use simple curricula to get robust policies. The curricula in question here were random shifts, domain randomization, using a few randomly sampled examples, and only shifting a single variable that causes high regret in isolation. There are works that obviously design this sort of curricula with adversarial methods or with regret-guided methods. But the point here was that you could get the same results with a very simple curriculum as long as you use a factor-study presentation. And yeah, obviously the future work here is how we can also design our own curricula in a much more advanced way with the factor-study presentations. Right. That's it pretty much. I'm going to go to the chat now. See if there's anything. Sorry. How did you get the factor-study presentations? Right. So in this case, there is multiple factor-study presentations you can define. For example, you could use only the distance matrix plus where the agent is. You could use all these variables. It doesn't really matter. How do you discover them? This is a fundamental problem in reinforcement learning. In this case, we provide this factor-study presentation to the agent. This reminds you maybe of variation autoencoders or disentangling representations or something like that. That is the general idea. You would want in general to learn this as part of learning the task. But yeah, in this case, we just provide it to the agent. Do you have a certain percentage of inputs that take high risk, or is it random? What do you mean by certain percentage of inputs that take high risk? What does an input that takes risk mean? Gonna wait a bit to see if he responds. Okay, I'm gonna try to interpret your question then, because right. Can you explain once more again what the sharp drop is? Yes, of course. 550. I think you mean about this, yeah. So on the left side, let me go to the presentation mode again. So in these experiments, I always have like a dotted line, which represents changing from training to testing, basically. So in this particular case, on the left side of this, I'm training using the curricula that I explained. For example, the pink one, I don't know if you can see, it's the second from the bottom on the left. It's using shuffling through 10 examples, for example, or 15 examples. The one on the top of it is training by changing the goal variable on each episode. So on each episode, it changes where the goal is, but everything else is the same. The one on top of that, it changes where the holes are on each environment, on each episode, sorry. And then on the right side of the dotted line, it's basically domain randomization. So it's random shifting. So on each episode, we're sampling a random grid. Like, so the agent could be anywhere, the size could be anywhere, the whole locations could be anywhere, etc. So this is kind of like training and testing, if that makes sense. Do you have? Thank you. Do you have certain percentage of input that take high risk, or is it random? I'm trying to understand what you mean. Did you ask it here, maybe? So generally speaking, yeah, maybe what you're asking is whether we are assessing how difficult or how risky some of the tasks are, or how some of the inputs are. We only assess whether there is a path to the end or not. We don't assess whether it's too easy because the agent location and the goal location are next to each other. Yeah, perhaps a more investigative look into this could do something like that, but we don't do it. Yeah. How is C able to generalize? let's see. How is C able to generalize? So C, the point with C is that on each episode you're seeing a different environment. The question is maybe how. I think the environment is able to learn because it has a good stage representation. But here the generalization is just IID, right? So you're sampling from the same distribution you're using for training. So obviously it's gonna generalize similarly. It's gonna have similar performance as you see. Sorry, as you see here is the bottom one on the left, but the top one on the right. So the training, the set distributions are the same. The question is maybe how is it able to learn so well when the PPO agent is unable to learn, the DQN agent is unable to learn. I think it's purely because of it has a good state representation, and the task is easy enough. Probably in a harder task, dominant randomization will be hard. If on every single episode you have a different environment, maybe you're never able to learn anything, and maybe it makes more sense to swap the task only if only after a few episodes. But then again, this doesn't reflect the scenario that I'm looking at in this paper and also in generally in my PhD, which is the environment changes all the time. As in the world, the environment changes all the time. In the world, you could design your own task. You could place, I don't know, your notebooks here and there, but it's never going to be exactly the same. And that's kind of the general motto of my research, basically. Right. These are the questions, I think.
Could you talk a bit about exploration versus exploitation in this context, or how will that work?
Good question. Exploration versus exploitation. I think I'm going to go back to. Sorry, I'm going to go here. Right. So in this case, in this particular task, exploration might mean. So just to give you also a context of exactly how much the rewards are, there is a +10 reward for the gift. There is a -10 reward for the whole. So this is like the two goal states. And there is a -0.1 reward for each step. So in this particular case, exploitation would be this behavior that we see in the horizontal line, which is, I know I can avoid getting a -10 by falling into a hole by just going left, right, or just hitting a wall all the time. And exploration would be trying to find where the goal is, where the present is. It doesn't seem that maybe that's actually something that I didn't mention in the paper, but good that you asked me. I did try to get a PPO agent and just give it as much exploration bonus as possible. So it tries to always find the goal, but it still doesn't manage to generalize when the environment changes on every episode. Yeah, the state is just too dense, maybe. But yeah, in this context, exploration versus exploitation would mean trying to find the goal, which is in one square, and you might fall into a hole while trying to get there, versus you know that maybe in a small region you will never lose, and you just go around in the region and you never lose. That would be, or you know how to get to the goal, so you exploit and you actually get to the goal. Yeah. In that case, I think you would also always go to the goal. Yeah.
Mm-hmm. Thanks.
Are there any other curricular learning strategies that could be explored in the? Yeah, there are. Read my next paper or talk to me. But yeah, there are more things you can do. Obviously, yeah. Simple or not, there are other things you can do. The reason we chose these ones here is because they're simple and they're easy to understand, and they achieve. I think there was one more that performed similarly, which was changing a random variable. I think changing a random variable on every episode performed similarly to those. But also these kind of the methods we presented kind of are a stepping stone for what I'm working on next. So yeah. Sorry, I can't tell you more, but you can talk to me. Maybe I'll tell you more. Right. Anyone else? Anything else?
I have a question regarding the curriculars. Can you show me the plots?
Yeah, sorry.
Uh, I was asking about the C, right? C is domain randomization, as you said earlier.
Yeah, yeah.
So, I mean, how is it able to like you know perform well uh, in just 550 epochs? Is it because the environment is simple, or because of the factor representation?
Is your question why is it able to keep performing the same, or why it
Yes.
learns?
Yeah. So,
So
I mean, probably. Yeah.
I should also mention, by the way, that in this graph, if you look at the bottom axis, it doesn't start from 0. It starts from 500. But I cropped it because it's just the interesting thing to look at here was how it transfers rather than what's the learning curve. But yes, it's able to perform well because it's IID generalization, while for everyone else, this is out of distribution generalization. And B, yes, I do think it's because of the factor state representation. Yeah, the factor state representation. Sorry, the factor state representations helps a lot because imagine that there might be different states that are symmetrical, and the neural network will be able to very easily take advantage of that when it's factored versus when you have an image that's factored. Right? Like in these factor representations, the reflection could mean just swapping two numbers around, for example. So yeah, I do think the factor state representations play a big role, and also we weren't able to get any good results without them.
Right. How many environments do you have? And like, how many environments are you sampling over the domain randomization part?
So in each episode, you sample a new one. So, and in this case, an epoch is 900 time steps, and an episode, a successful episode, is maximum. Don't remember because I think I limited the grids to 20 by 20. So maybe 50, 60 steps maximum. So
So,
50 steps, sorry.
I mean, so you mean that I can get only 20 environments? I mean, 20 different tasks at each time step?
So at each time step, you get one task, yeah?
Over 20 tasks?
Over what?
Over 20 tasks? You just have 20 tasks and you are trying to get one task at each time step randomly?
So we're talking about domain random shifting, yeah, C.
Right, yes.
So on the start of each episode, we go here, sorry, we go to each of these 4 variables that have a red star, and we sample them. So there is a huge number of them because the whole locations, imagine there is 2 to the n possible, but a lot of them are invalid because there is no valid path. And if it's invalid, we sample it again, basically. So there is a lot of possible tasks, way more than 20. There is 20 different grid sizes, yeah. But the whole locations are like, it's an extremely high dimensional space. Yeah.
Right.
Exponential.
All right, thanks.
Oops. Sorry. What's going on? Oh.
Yeah. If no one has any questions, we can thank the speaker.
Thank you for having me.
Thanks, Pani, for joining us today. It's a really interesting work. We'll definitely connect you offline.
Thank you,
You.
guys.